Okay, welcome. So this review session is largely going to be focused on glaciers, which are the topic of lectures 11 and 12 released last week. There is going to be another review session next week on Monday, May 17th that will be specific to lecture quiz number 2, which is going to open next Monday, aka May 17th. And this week, there are a handful of presentations happening that are extra credit opportunities. And this is just a bit of also an overview of where we are in terms of upcoming assignments. So I mentioned lecture quiz number 2, and that is going to open next Monday. And I will host a review session specific to that on Monday, May 17th. That's going to cover the 2 Glaciers lectures, as well as lectures 13 and 14 on the history of Antarctica, which I am releasing this week. And then in terms of reading and videos, there is a short excerpt from one of Sir Ernest Shackleton's books that is linked on Gaucho Space for you to read this week. You don't need to read that in depth. Skimming it is fine. And then there are some excerpts of the movies Encounters at the End of the World and Antarctica: A Year on Ice that you will want to have seen before you take the lecture quiz, but that is not till next week. There is a lab due this Friday on glaciers, and I hope that some of the material in this review session will be useful for that. I will also have a slide near the end detailing some particularly pertinent points related to glaciers that I think will help with the lab. And although reading assignment number 2 is not due until Sunday, May 30th, I am encouraging people to get a head start on that if they can. The reading assignments should only take really a couple hours to do at most, finding the article, taking some notes on it, and then it's about a 1-page response. So that's something that you can knock off ahead of time if you'd like to. It is due the Sunday before Dead Week, because technically we aren't allowed to assign any work during Dead Week. Now that's it for the upcoming required assignments. There are a couple of opportunities for extra credit coming up this week, actually. There's 3 in total, so lots of great talks happening related to UCSB. There are 2 UC Santa Cruz seminars being hosted, one by Daniela Rimpe from Texas and another by Michelle Thompson from Purdue University in Indiana. One talking about the connection between cracks in the rock and the circulation of water and carbon, which is relevant to climate change, as well as the other one on erosion of celestial bodies, aka how asteroids and celestial bodies with not much of an atmosphere break down. And there is also a UCSB colloquium happening this Thursday. We have a visiting professor talking about earthquakes. So the Zoom link for the colloquium is here, and the information for the 2 UC Santa Cruz seminars is in the class announcement for Monday, May 10th, if you would like to attend any of these. Now, as for reading assignment number 2, you've seen these slides before. You've seen this particular slide before is what I meant to say, but it is very similar in format to the last assignment. It is 400 words or more, except that this time you are picking an academic article to write about rather than an article that appeared in a news format. So this is actually doing a report on a bit of published research by the actual researchers themselves. And it has to be relevant to Antarctica, and probably most of you will be picking out scientific articles. However, there are some parts of this class that touch more on history and social science, and if you find interesting historical academic articles about Antarctica, that is also acceptable. And you can find journal articles on Google. You can also find them by using the UCSB libraries databases, or the ones that you have access to via your UCSB credentials. You can go to the UCSB library website, log in, and then you can find their databases page. And there's a lot of different ones you can use. If you're looking for geology, GeoRef is a good one. But if you're interested in something related to biology, there's some databases that collect biology articles. The nice thing about these databases is that they are databases for research. So Google is going to get you a whole hodgepodge of stuff, and you're going to have to sift through that. But the databases pop up just research, basically. So I'm happy to suggest articles if you have a topic you're interested in. I'm happy to take looks at articles and see if I think it's a good fit. It does not need to be a super dense or a super long article. The only things in your reply that have to be in there are you need to address what kind of research the authors were doing. So I recommend against picking articles that are summaries of other people's research. And then what were the results that the authors got, and why are those results important? And it doesn't have to be important necessarily in like an earth-shattering or earth-saving scale, but why are they important for the authors or to the field that the authors are studying? What interesting has come out of this paper? And lastly, were the results what the authors were expecting? Because usually, almost always, the authors will make some sort of prediction in their paper to sort of see if they can predict what's going to happen. Like they'll place their own prediction as to what they expect to see from the data or from the study, and they will address whether that was actually what they saw in their discussion. And also make sure that there's a link to the article. So before I move on to talking about the actual lecture content, does anyone have questions about upcoming assignments or anything of the sort? And you should be able to see your midterm grades if you have not already looked. So moving on then, in lecture 11, we learned about how glaciers fit into the overall water cycle, how frozen water is actually where most of Earth's fresh water is. And then we went into the definition of a glacier. It's compacted ice with less than 20% air that is moving under its own weight, moving like a river. Glaciers function as rivers of ice, essentially. So that's one reason why I emphasize them being part of the water cycle, because they take the place of rivers largely in Antarctica. You do have some rivers and lakes in Antarctica. You get those lakes and rivers forming under glaciers because with high enough pressure, you can melt ice at a lower temperature. It's possible to have liquid water at colder temperatures. So you do get some lakes and rivers under the very thick ice sheets. But volume-wise, there is not a lot of liquid water in those lakes and rivers compared to the overall mass of glaciers in Antarctica. And the glaciers in Antarctica are continental glaciers. They are a type of glacier where the ice covers just about everything and covers just about everything in their path until the glaciers start to reach the edges of the continent. Continental glaciers are known as ice sheets if they are larger than 50,000 square kilometers. So the only true ice sheets we have are the two separate Antarctic ice sheets and then the one covering Greenland. You do also have some smaller ice caps in places like Baffin Island, Canada, or Iceland, where there's just a smaller remnant of what used to be a much, much bigger ice sheet. Because we are technically living in an ice age, we're living in a relatively warm period of this ice age known as an interglacial period. So most glaciers in the world are non-continental glaciers. And one thing I will mention actually is that glaciers can change, what type of glacier they are changes in different parts of their course. Kind of like how rivers are going to be fast early on and slow and muddy and meandering by the time they reach the ocean. Glaciers will start as one type of glacier, and at the point where they stop flowing or end, they're going to be a completely different type of glacier. For example, this Piedmont Glacier here hasn't always been a Piedmont Glacier. The Piedmont Glacier portion just refers to the ending portion where my cursor is. It is flowing out of the East Antarctic ice sheet. So that's an example actually of how the flow from continental glaciers can continue on into non-continental glaciers if part of the ice starts to flow through a valley and gets constrained by that valley. And what's happening here is that this Piedmont Glacier is where glaciers that are being channeled through a pretty narrow valley get the chance to spread out, and they dissipate after that because the ice is more spread out and there's more surface area. So alpine glaciers are non-continental glaciers that are up in the mountains. Cirque glaciers are a particular type of alpine glacier that form in this bowl-shaped valley, and that's often what form glaciers are in when they first start forming in the zone where they first accumulate. Valley glaciers are slightly more spread out glaciers that are flowing through valleys. Piedmont glaciers are when a valley or alpine glacier is allowed to spread out after flowing through a pretty narrow area, and it makes a fan-shaped flow like this. And then an outlet glacier is any glacier that reaches the ocean. A tidewater glacier is one type of outlet glacier where the movement of the glacier is actually affected by the movement of the tides. When the tide is high, the buoyancy of the ocean water pushes up the glacier, causing the portions of the glacier that are further inland to flow a bit faster. But when tide is low, that buoyancy is lost and the glacier is once again experiencing friction with the ground and flowing much more slowly. And friction plays an important role in how fast glaciers move. Glaciers will flow at different rates depending on, well, a glacier will flow at different rates in different portions. So the sides of the glacier will flow more slowly than the center of the glacier because the center is not experiencing the friction with the rock in the valley walls and on the valley floor bottom that the sides are experiencing and that the bottom of the glacier is experiencing. And also the type of rock that the glacier is flowing over can make a difference. That can more resistant bits of rock can cause disturbances that can cause brittle failure and crevasse formation. And then also some types of rocks, if they're more resistant to flow, can kind of slow the glacier down as they're flowing. So any questions about any of these terms? Or about anything that I touched on just now? Glaciers flow from the center of the continent and Antarctica out to the edge. And the East Antarctic ice sheet experiences divergent flow, where the snow is accumulating just about at the center of the ice sheet and then flowing out in all directions towards the coasts in all directions. The West Antarctic ice sheet has convergent flow in which most of the ice flows into the same ice stream and exits at the same point in West Antarctica. And an ice stream is a portion of a glacier that moves faster than the rest. It's often noticeable in large ice sheets like those that cover Antarctica because satellites can monitor how fast different areas in the ice are moving relative to one another, and they can detect that there will be areas in which the ice is channeled into and moved towards the coast fastest. Ice streams will generally form where there is the least friction. So on a big scale, like when you have an ice sheet covering everything, the ice streams might be more likely to form if they are flowing over where the rock is a bit less resistant to erosion and thus where there is less friction. And the ice sheets, remember, since there is so much pressure from them, the high pressure allows some liquid water to exist at the base of some of these glaciers. So you do have some lakes under the ice, like Lake Vostok, and you also sometimes have channels or basically subglacial rivers connecting them. But most water in Antarctica is still transported by glaciers in frozen form through ice streams. Ice streams may turn into ice falls if the steepness suddenly changes, the same way that rivers will flow into waterfalls when they flow over steep cliffs, over big changes in topography, basically. The cool thing about the Antarctic glaciers is that since the snow is still accumulating rather than ablating along the Antarctic coastline, the glaciers continue to flow over the surface of the ocean. And they take the form of an ice shelf when doing so. The ice shelf is the direct extension of the ice sheets that are lying on the land. These ice shelves will undergo what is known as calving, or the breaking up of ice, and icebergs form from the ice shelves calving. Icebergs are broken off from the ice shelves. Now, again, sea ice doesn't refer to the ice flowing from the glaciers. The glaciers are forming on land, and the ice from the land just flows over the ocean because it doesn't start to melt immediately along the coastline. I will say that it does start to melt over the ocean faster than it does over the land because the ocean does a good job of conducting heat to it. Also, something to consider is that with global warming, the oceans are getting warmer, and that's playing a role in some of the ice sheets, particularly some of those in West Antarctica, starting to see larger than normal calving episodes, episodes in which pieces as large as some of the smaller US states start to break off. Sea ice forms on the ocean, though. Sea ice is a completely separate phenomenon. It forms from seawater freezing. And remember that seawater formation plays into Antarctic bottom water formation, because when some of the seawater freezes, the salt doesn't go into the ice. The ice is fresh water. The sea ice is fresh. So the ocean water that is left behind, there's a smaller amount of it, but with the same amount of salt that was present before. So that makes the water denser. And that's just a connection to consider between this unit and the ocean circulation unit earlier. The next slide, I'll talk a little bit about the difference between warm base and cold base glaciers again. Any questions up until this point? And I have this exact same slide in one of the lectures, but I wanted to include this here because it's a bit of a nuanced definition, and when I first started teaching this course, it took me a little bit of time to understand exactly what was going on here. So remember that we can define glaciers either based on their shape, which is dependent on what sort of topography we're dealing with. So valley glaciers, continental glaciers, alpine glaciers, and the like. Completely separate to that, there is a way to classify glaciers based on their thermal properties. And the cold versus warm base glacier distinction has to do with whether there is much meltwater, especially at the base of the glacier, but whether a significant degree of meltwater can exist anywhere in the glacier. And the term pressure melting temperature indicates that the temperature at which either ice melts to liquid water or liquid water can melt to form ice, that temperature changes depending on the pressure. And that's what I mean when I say that liquid water can exist at lower temperatures under higher pressures. Because you see what happens is that the top scale, the x-axis here, the horizontal axis is temperature. And you'll see that 0 degrees Celsius under relatively little pressure is about, that's the freezing point of water. As you increase the pressure, though, you'll notice that the melting point drops below 0. That means that you can, under high pressures, be at about, say, -1 degree Celsius and still have some liquid water. And the key thing to consider is this is a phase diagram, and you don't really have to worry too much about what a phase diagram is, but the boundary on a phase diagram is showing you at what combination of pressure and temperature both phases can exist. Along this line, so this line represents, each point on this line is a different combination of pressure and temperature, because the pressure is going to increase with depth in the glacier, remember. Each point on here indicates a pressure and temperature at which both liquid water and frozen water can coexist to some degree. And how this comes into play with glaciers. So notice that the pressure melt temperature line is the same on both of these two diagrams. That's just a property of water. However, the other line is different, and those are the ice temperature lines. This shows, the diagram on the left shows you how the temperature of a glacier goes from the top of the glacier to the bottom of the glacier in Antarctic glaciers or cold-based glaciers, while the diagram on the right shows you how the temperature in a glacier goes from the top to the bottom in a warm-based glacier, or a glacier found in mountainous areas of more temperate latitudes, like glaciers you'd find in the Himalaya, those you'd find in the Andes, in the Rocky Mountains, or in the Swiss Alps. In Antarctica, remember that the sun is very weak. The polar sun does not do a very good job of heating the ice, and so the bottom of the glacier is actually somewhat warmer than the top of the glacier. However, even with that little bit of heating from the heat of the Earth at the bottom of a glacier, the ice temperature is still colder than any points along the pressure melt temperature line. So cold-based glaciers like those in Antarctica do not form very much meltwater, and that means that their flow is not very heavily lubricated by liquid water. Liquid water reduces friction and helps glaciers move more smoothly and gently, and also allows basal sliding to occur. It allows the glacier to slide forward as a block. Now, if that meltwater is present, the glacier can slide forward as a block. It can experience basal sliding. That is much more common in the glaciers that you find in the Swiss Alps or in Glacier National Park, because it's going to be warmest at the surface there because the sun is heating it most efficiently. And it turns out that the ice temperature line from the top of the bottom to the glacier just about follows the pressure temperature line. So throughout the glacier, in a warm-based glacier, you can have a fair bit of meltwater forming, and that meltwater helps lubricate the glacier. So that's the importance of the distinction of cold-based versus warm-based glaciers. Cold-based glaciers are often known as polar glaciers, and temperate glaciers, so they form in, so the Himalaya or the Andes, those are latitudes that are temperate and that they're getting a lot more direct sunlight than Antarctica is, and that's what allows the surface of the ice to be a bit warmer. Temperate glaciers, the glaciers in Glacier National Park are going to be warm-based glaciers. Those you find up in the mountains in the Andes are going to be warm-based glaciers. It's cold because the air is less dense up there, but you still have pretty intense sunlight that is heating the surface of the glaciers. And this has to do a lot with latitude, because in Antarctica, yes, closer to the equator, precisely. Closer to the equator than Antarctica, certainly. And remember that the closer you are to the poles, the weaker and more spread out the sunlight is going to be. And that is the case in Antarctica. Are there any other questions before I move on past this slide? We also talked about how glaciers move. Glaciers can either move as a single cohesive mass, and that is more common with warm-based glaciers. Glaciers can also flow like a very thick or viscous fluid downhill, in which the ice in the glacier will deform slowly. Now, if glaciers are under a lot of stress, such as if they flow around a bend relatively suddenly, or if they flow over a mound of more resistant rock, they will form crevasses. The ice will not be able to rearrange fast enough to avoid the ice breaking and forming cracks, and those cracks are known as crevasses. And crevasses form as a result of brittle failure, when plastic flow gives way to breakage, which is what I mean by brittle. And this is something you'll investigate a little bit in the lab using the model of the sort of thick flubber solid model that I briefly showed you the video of in lecture 12, and that you'll see again when you do lab number 6. And you basically want to remember that glaciers can move in one of two ways. They can move under low amounts of stress. They will move more like a liquid. They'll flow more. Under higher amounts of stress, they'll break. And the more meltwater there is, the more that the glaciers will simply slide forward as opposed to deforming over time. I would say those are the most important points regarding the movement of glaciers. Before I move on to erosion, does anyone have questions? So the last topic we went over was glacial erosion, because since glaciers take the place of rivers by and large in Antarctica, in the other continents, rivers are a major agent of erosion, the removal of rock and soil and the carving of the land into valleys and canyons. And there is very little bit of liquid water erosion in Antarctica, and there is also some wind erosion in Antarctica. There were a couple slides in the lecture about ventifacts, which are these cool sort of horned skull-like features that you get from the wind sculpting them, especially in places like the dry valleys where the katabatic winds are strong. But for the most part, the main agent of erosion in Antarctica is glaciers. And glaciers are by and large very effective agents of erosion because they bulldoze everything out of their way, essentially. And large ice sheets like those in Antarctica in particular have really very heavily eroded and scraped down the bedrock underneath them as they flow downhill. Glaciers can either pluck, and that is a process that forms when pressure builds up underneath the glacier, allowing meltwater to form momentarily. And this can occur in either cold base or warm base glaciers. It is a little bit more common in warm base glaciers because it's easier for the liquid water to form. But it can happen in Antarctica. The pressure can build up enough in Antarctica for you to get a little bit of meltwater forming where the glacier is flowing over, for example, a mound of rock that is very resistant to being eroded down. When the glacier reaches the other side of that mound, when it's no longer experiencing as much resistance to flow and resistance to erosion, that will cause the pressure to very suddenly drop and will cause any meltwater to freeze. And the frozen meltwater will sort of glue the glacier to the rock, but since the glacier's overall momentum is forward, it rips a bit of the rock away from it. It takes the rock with it and plucks bits of rock. The sediments eroded by glaciers are mostly fine-grained, but there's a mix of larger pieces of rock, and a lot of those larger pieces of rock are from plucking. For the most part, outside of plucking, glaciers simply remove material by the slow sort of sandpaper-like smoothing of the rocks underneath them. The rocks being eroded by glaciers are very smooth, and that's actually one bit of evidence we often have that glaciers have been present in an area when we're looking at the rock record, or even when we're simply looking at the surface of rocks and we can see especially smooth areas of rocks as evidence that this area was recently glaciated. It's something we see a lot in rocks in Canada, because Canada was entirely covered by ice sheets during the most recent glacial maximum within the current ice age we're in. Abrasion by glaciers will leave these polished surfaces, like I just mentioned. They'll also leave striations if the glacier is most intensely flowing in one direction, so it'll leave these little lines on the rock indicating flow. And if a glacier flows over the rock long enough, it can actually make these grooves in the rock, just like heavy use of a road can create ruts in that road if the cars are all driving over the same point in the road. So glaciers do carry some material on their surface that's known as ice rafted debris, because whatever falls on a glacier kind of just gets carried along with it. The term for the sediment that gets pushed by glaciers and deposited in the terminal moraines, these hills at the ends of glaciers where all of their stuff is piled, this sediment is known as till. It is mostly very small grains of sediment, mostly that's been ground up by the glacier, but it's very poorly sorted because it still has a number of larger particles and larger sediment sizes in them. Like, it's going to be mostly sand and mud, but there's going to be some pebbles and boulders in there from plucking, and also from boulders that might have fallen on the surface of the glacier and that would have been carried by the glacier and just dropped off where the glacier melts completely. Till becomes diamictite when it lithifies. Now, when a glacier ends on land like this, which is not as common in Antarctica because the glaciers flow over the ocean, but when the glacier ends on land like this, it'll produce all this sediment piled up here. The water that is melting and coming from the glacier will carry some sediment with it, and that is known as outwash. That outwash is going to be very fine-grained. It's going to be silt, like muddy silt with a little bit of sand maybe, but that's going to be because the meltwater is flowing slowly and doesn't have a lot of energy. So it's just carrying some muddy sediment, some very fine-grained tiny sediment away, because slower moving water only really has the energy to carry tiny particles. And on that front, the outwash, and varves are a particular type of pattern that forms with outwash deposits. They form in areas where in the summer, greater heating will produce more meltwater, which will carry more outwash into a lake. And the outwash tends to be yellow, white, light colored because it's very heavy in quartz that's been eroded by the glaciers. In the winter, since there's not as much meltwater, there won't be as much outwash ending up in the lake, and the sediments will be more dominated by dark-colored lake muds. So the varve patterns, if you go back to the slides, are these alternating black and white layers that show seasonal deposits from glaciers. Glacial flour is when quartz is ground down to really, really tiny amounts that it gets suspended in water. And you'll find glacial flour suspended in bays and in lakes that get a lot of meltwater from glaciers, and those lakes and those bays will have a turquoise color because when the water has a lot of quartz in it, that makes the water look turquoise because of the optical properties of quartz. And that's a really cool thing that you will learn more about if you take more geology classes. Different minerals have different optical properties when you have them as a large piece and when you have tiny, tiny amounts of them, which is one reason why geologists look at rocks under thin section. Lastly, erratics are large pieces of rock, boulders left behind by glaciers that have since melted. Dropstones are they're large plucked pieces of rocks that are carried on the underside of ice shelves like those in Antarctica. As the ice shelves start to melt, the dropstones fall out of the glacier into the ocean, onto the ocean floor. The ocean floor is made of, it's kind of like the lake sediment I described before. It's dark colored mud. You'll have these nice, mostly horizontal layers of ocean mud, and then you'll just have this large boulder in the middle of it. And that is what a dropstone is. And it's in the rock record, it's powerful evidence that glaciers in the area that's being sampled were existing at sea level and actually had ice shelves that went out to sea. So that was a lot. This bit was about half of a whole lecture. But any questions about erosion or the different types of erosional products of glaciers? So the last slide I have is some tidbits on what to do for this week's lab if you haven't already started it. And lab 6 is quite closely related to the lecture material, so I would highly recommend reviewing and rewatching lectures 11 and 12 before attempting the lab if you haven't already seen them. But here's a few specific points that I think are especially important to consider given the lab questions. You always want to think about friction when you think about glaciers flowing. The parts of the glacier that are touching the rock, whether that rock is in the valley, like the sides of the valley, or underneath the glacier, those are going to experience more friction. If ice, remember, you want to think about how the ice in the glacier is kind of, the individual crystals of ice are all moving at different speeds. In the center and on the top of the glacier, the ice is mostly just going to be bumping against other ice, like other ice in the glacier, and that causes less friction than does ice scraping against rock. So that's why you get ice streams forming in the center of glaciers, and also in parts of the ice sheet that are really thick, where there's a lot of ice between the top of the glacier and the rock. Another point I wanted to bring up is that this lab does a bit of an application of both biology and of something we briefly touched on during the geology unit. During the geology unit, I talked about how you can date rocks either by comparing their placement to other rocks, relative dating, or you can actually get, you can take measurements of uranium and lead to use radioactivity to figure out how old the rock is. You can do that with carbon and some organic remains. It's possible to do that with mummies or with bits of fabric that have bits of fabric from archaeological sites or bits of skin. And speaking of mummies, remember how we get these seals that just wander up in the dry valleys for no apparent reason and then become mummified by the dryness. This lab has you measure how much some of the glaciers have retreated, and you figure out some of the points in time using carbon dates obtained from these seals. Carbon dates that indicate that, for example, the seal was crawling around here around 500 years ago, for example. The key thing to remember with this lab is that if a seal mummy is there, and we come up with a date saying that, oh, that seal is about 500 years old, that means that around 500 years there were no glaciers there. If the seal is there, if the seal is there at a given time, that means that there was no glacier there at whatever time the seal happened to wander up. So consider that for some of the questions on glacial retreat, and it's kind of a cool application to use the dates for when these seals died as a way to bracket when the glaciers retreated, because the presence of the seals tells us that there were no glaciers there. And on that note, the lab has you study glacial retreat and how fast some of the glaciers are getting smaller in size. And for any rate, you'll want to remember that for a lot of rates are something happening over time. The rate of glacial retreat is the distance that the glacier retreats back over a given unit of time. And in the lab, you'll want to use the scale that the TAs provide you in the pictures you'll use. And then you'll use some of the dates that you obtain from carbon dates obtained from these seals to figure out how much time it took for the glaciers to retreat. I only really briefly touched on tidewater glaciers, but there is a question in the lab related to them. And you'll want to remember that tidewater glaciers are vulnerable to climate change because they touch the ocean, and the ocean is getting warmer with global warming. That's something I've talked about and which you probably all at least are somewhat aware of from the news. I'll talk more about it in class formally the week after this when we do climate change. So that is about all I have for today. Does anyone have any more questions or thoughts before I close the presentation for the day? Oh, and this was a picture I took from one of the helicopters. This is an iceberg that broke off from one of the ice shelves, and this is just sea ice. So it kind of looks like it's just ice surrounding other ice, and it is. It's one type of ice that broke off from land ice that's being surrounded by sea ice. All right, so that's the presentation for today. Oh, do I see a question? Yep. Thank you, and thanks for coming. And there will be a presentation for lecture quiz number 2 next week. And I'll be releasing the lectures later tonight, or releasing lecture 13 later tonight, that is.